Okay, welcome class. Today our lecture is going to be on empirical and molecular formulas, how to solve those types of problems, and what to do when you're trying to find a formula from percent composition or from mass. So we'll actually do this in lab. It's actually really a cool concept. We'll do all sorts of practice on this, and this will be our first formal lab report in AP Chem. So let's get ready to rumble. Okay, so this was on the very first chapter, but you're going to run into this a lot. So it's good. It's an important concept to know. So a molecular formula, this would be something like this. So they're going to give you the whole thing. So like H2O2 is hydrogen peroxide. So this is like the formula in its whole form. Okay. Now, when you're dealing in a lab situation, what happens is sometimes we work in ratios. And if I were to look at this simplest whole ratio, I would get the empirical formula, which is the simplest formula, as HO. Okay, so you have to kind of watch out when dealing with formulas, because sometimes what they're dealing with is they'll be dealing with the molecular formula. This would be like your actual formula. And then the simplest formula, or the reduced ratio, would be the empirical formula. So for example, if we have glucose is C6H12O6, and we know that as the molecular formula, the actual formula has a molar mass of 180. That is the molecular formula of glucose. Now, if we reduce it down, you can see that we can take the 6 out, and you'd see CH2O would be the empirical formula, the reduced formula. Okay, so keeping that in mind, that's what we are talking about when we distinguish between empirical and molecular formula. And you are going to be finding the empirical formulas today, and also sometimes the molecular formula if they give you some information in the problem. So what does this look like? Let's take a look. Okay, I got to go this way. Okay. All right. So here's an example. So if we're talking about molecular formula, empirical formula, sometimes the molecular and empirical formula are the same. So in this case, if I'm dealing with this one right here, H2O, the empirical formula is already reduced down because there's a 1 here and you can't reduce it anymore. This one, on the other hand, the second one would be CH2O, which would be the same molecular form or empirical formula as this one. Now you can see that these would have the same these two would have the same reduced empirical formula, but their molecular formulas are different. So keep that in mind, that it can be different. We'll kind of look and distinguish them. And so this one would also be CH2 as we reduce it down. Okay, so molecular formula and empirical formula, they can be identical. You can also scale them up, scale them down. Just because they have the same empirical formula does not mean that they have the same molecular formula. Very important to know. Okay, now after you analyze a compound, here's what happens. So you're going to be in lab, you're going to make stuff, and you're going to be able to figure out what the masses of each one are. And since we know the masses, you can actually figure out what the formula is, or empirical formula, from the masses of the stuff found in a formula. Okay, so let me go here real quick. So I'm going to go back and just kind of talk about this percent composition thing. So if I have an element, a compound H2O, the percent composition is like how much per each element is present compared to the molar mass of the whole element. So for our whole compound. So this one has a mass, this whole formula, H2O, has a mass of 18. Okay, and the mass of hydrogen in this compound is 2. So when we're looking at the mass percent of this one, so it would be 2 divided by 18, that's like 11%. So it's 11% hydrogen and 89% oxygen. And from that, we're able to figure out the formula if we can kind of do some nifty calculations. So these are called the mass percent, or the amounts of each part of a formula. And from that, we're able to figure out the subscripts and all that other stuff in a formula. Okay, now a couple things. If you're going to find the empirical formula, you have to assume that if they give you the percents, that you just directly turn the percents into grams. Because let's just assume you have a 100-gram sample of water. 11 grams of it would be hydrogen, and 89 grams would be oxygen from the previous example. So just convert percent into grams. Next, you're going to always use those red numbers on the chart. Those are the molar masses, the atomic masses of the elements. And then we're going to kind of talk about this, but you have to figure out which of these mole values is the smallest once you get there, and you compare ratios. At the end, you just find whole numbers. So sometimes you're going to get fractions or decimals, and you have to multiply to get into whole numbers. I'll show you some examples of that. Okay, so, and this is just it, use whole number results as subscripts and write the empirical formula. So sometimes, and this is a good point, sometimes they get really, really big if you're talking about a large organic molecule. Okay, so there's a following poem. Poems are good. Percent to mass, mass to mole, divide by small, multiply to whole. So say that a few times fast. Percent to mass, mass to mole, divide by small, multiply by to whole. Okay, so let's give an example of this one. So to start off, okay, so everything has to eventually be in moles. When you don't know what to do in chemistry, randomly find moles and you're right half the time. So these ones, these percents here that we're talking about, let me go back. What you need to do is you need to convert these into moles. So I'm going to go here and I'm going to assume that 54.93 grams of K. Okay. And then we look on the chart and we find out the molar mass of K is 39 grams in 1 mole. Okay. So we're going to find moles. So 54.93 divided by 39. If you have a calculator, follow along on your own. You get 1.41 moles of K. And now we're going to repeat with boron. So boron is 38.73 grams of B. And you look up on the chart and you find that boron is 10.81 grams in 1 mole. So I'm just going to make note, be careful, because these are whole ratios, you can't round too much. So I'm just going to kind of be careful with my rounding on the molar masses. Sometimes you can get away with it, but sometimes in these problems you'll be far off. So that's just my pro tip number 1. Divided by 10.81 gives you 3.583 moles of B. And then we'll do the last one with hydrogen. So it's 3.34 grams of H, and that's 1.01 grams in 1 mole of H. And so, I mean, that's pretty much 6.34, but let's just play around with it. All right, so 6.278 or 2.8. There we go. All right. Now, at this point, you find the smallest value, and that becomes the thing that you use to find the ratios. So in a formula like the subscript H2O, this actually represents how many moles you have. That 2 says you have 2 moles for every 1 mole of oxygen. So what we know here is if you look at these ratios here, you can find out that they kind of have a relationship. So for example, this is going to be 1 because 1.41 divided by 1.41 is 1. This, if we take the second one divided by 1.41, so we're comparing it to the ratio of the other one, I imagine you're going to get pretty close to 2. 0.58 divided by 1.41 gives you 2.5. Okay, so that's important, 2.5. And then this last one, if we do that divided by, so 6.28 divided by 1.41 gives me about 4.5 moles if I rounded pretty close. And so now what I know is that I have K and there's 1, and then B and there's 2.5, and then H and there's 4.5. Okay, so this is the part where what you have to do is you have to kind of think, what number can I multiply all these back until I have a whole ratio, like a whole number? So I'm going to multiply this by 2. So I'm kind of running out of room here. So let me erase something. Get my little eraser here. I'm going to erase this business. Okay, much better. And back to the pen. So I'm going to get K2 B5, H9? And that is my reduced lowest number empirical formula. So what, again, if we look at the steps, if we go back, right? Let's go back here for a second. Oops, close this down. All right, if we go back, You take your percent to mass, right? That's what we did to start. We took the mass to mole. And then once we found those mole numbers, we found the smallest one, right? And we divided everything by the smallest one, and then we multiplied to a whole. So those easy steps are your best bet at solving empirical formula problems. All right, let's take a look at this one. And just a note, sometimes you're going to get, I'm going to go back to this one. So there's common fractions you're going to see. Like the first problem we saw 0.5. Well, you're going to multiply it by 2. 0.25 is going to be by times 4, and 0.33 or 0.67 is going to be by 3, because those are common solutions that you'll see when you do these types of problems. All right, let's do one last problem, and then we'll actually, I think there might be a couple more to do on this one. Okay, find the empirical formula for a compound that contains 26.8 grams of tin, 16 grams of Cl, and 57.2 grams of I. Now, you can also have a problem where they don't give you in percents, they give it in grams, and that just saves you a step. But basically, you start by getting all of these into grams, all of these percents. Okay, so I got to move this out the way. Perfect. So we have 26.8 grams of tin. Okay, and tin's molecular mass is 118.71 grams in 1 mole of tin. Okay, and then we have 16.0 grams of chlorine, and in 1 mole of chlorine there's 35.245 grams in 1 mole of Cl. And then finally, 57.2 grams of I, and then 126.9, 126.9, yeah, grams in 1 mole of I. So we do all of these real quick, and that's going to tell us our smallest one. So 26.8 divided by 118.71 gives me 0.2258 moles. I really don't do sig figs in these because, like, I'm comparing ratios. I just don't do it, because then sometimes you round a little bit off and it's a little bit more confusing. And then 16 divided by 35.45, plus when you think about it, like, you're trying to find the whole ratio, so you don't really need sig figs for these. I know it's almost sacrilegious to say, but it's just, you're trying to figure out the relationship between each other. Look at this. This is great. See how these are basically the same ratio? That means you have the same amount, the same number of moles of Cl as I. And the reason why they have different percents is the mass of their molar masses is different. Their molecular mass, the atomic mass is different. So you can almost just do this one just by looking at it. Do you see how this is the smallest? So the first one, we're going to divide everything by that. And this one's going to work out perfect. I love it when it's like this. This is going to be 1, and this is going to be 2, and this is going to be 2, right? So then you're going to get a formula, Sn, and there's going to be 1, and it's going to be Cli, and there should be none of that. But basically, whatever they give you, typically the order they give it to you is what you put in the formula when you're finally done. And there would be 2's here. And the reason there's 2's is the ratio was 2. Okay. All right. Let's keep going since we're having so much fun, and let's wrap this up here shortly. So I'm going to X this out, go here, boom. Okay. Now, remember how we talked about molecular formulas at the beginning? This is the last little bits here. So it's you have to do an experiment to find the empirical formula, and then remember the molecular formula is some whole ratio of it. Okay, so what you need is 2 things to find it. You need the empirical formula and the molar mass of the compound. So it's going to look like this. So you're going to find the mass of the empirical formula, and then you're going to compare that to the mass of the known mass of the molecular formula, and you divide to find the whole ratio. So let me show you. Okay, so take a look at this one. So they know for a fact that the molar mass of a compound is 180.50 grams per mole. And you also know the empirical formula is this, right here. Okay, so what we're going to do is the molecular formula is some ratio of that. So you have to figure out how much does this actually weigh? What is the molar mass of this empirical formula? So we know that C is 12, and there's two of them, so that's 24 plus 1 plus 35. And for these ones, you can kind of get the gist of it. In the previous problems, they say don't round, but you could pretty much round for these ones because it's a whole ratio. You can round for the empirical formulas. Your ratios might be a little bit off, but you get this as being 60, right? So now look, 181.5 divided by 60. So this is if you're comparing the molecular formula compared to the empirical formula, you can see that this is three times as large, right? So the actual molecular formula is C6H3Cl3 because we know that it's three times the amount. That's super nifty. Okay, I think we might be done. Let's see. Okay, now I'm going to kind of end the video. Maybe we'll stop and do this one together. But in this type of problem, what you have is they're telling you that it contains carbon and hydrogen, and they say how much carbon's in it. And so you have to subtract to find hydrogen. And then they give you a molar mass. And then how would you find the empirical formula? So we'll pause, we'll maybe do this together, and we'll talk about these kind of things. And then we're going to do some partner work and make sense of all this madness. I hope you're having a good day. This is Steve Woods signing off with another maybe not so good AP chemistry lecture. All right, see ya.